Usually when you talk about driving a car, there's this very direct mechanical expectation of how things work.
Right, yeah. A physical relationship.
Exactly, like you turn the steering wheel left and the tires angle left. You press the brake pedal and the pads physically squeeze the rotors. It's binary, it's clean.
What you input physically is exactly what you get out mechanically.
Right. But imagine you're driving, like, a modern car with an advanced lane assist, right? And suddenly, right as you're taking this incredibly tricky curving off-ramp, the car just hands the steering wheel back to you.
Oh, man.
But it does it in completely different ways depending on your exact speed. Or maybe it changes the steering ratio entirely just because, I don't know, a single sensor somewhere in the rear bumper happened to fail.
That is, that's a terrifying thought for a driver.
Oh, totally.
But it is the absolute reality for modern aviators.
And that reality is basically our mission for today's deep dive. We are cracking open a highly detailed instructor's masterclass on the Airbus A320 family flight control philosophy.
Yes, specifically looking at ATA 27.
Right, and we're diving deep into the nuances that A320neo and A321XLR pilots face. We're going to decode this fascinating, almost hidden relationship between human pilots and aircraft automation.
It's really incredible stuff.
It is. Like, imagine you're sitting in that left seat, your hand is on the side stick, and the runway is just coming up fast. We're looking at how modern fly-by-wire planes literally change their own rules mid-flight.
Yeah, and what's so fascinating here is that we often think of fly-by-wire as this single static state of being.
Like an autopilot button or something.
Exactly. Like you push a button, engage the system, and the computer just flies the plane.
Yeah.
But the core thesis of these masterclass notes reveals something entirely different.
Right.
Fly-by-wire is a highly dynamic relationship. The connection between the pilot's physical input on the stick and the aircraft's actual aerodynamic response is constantly shifting.
Because it depends on what the plane is doing at that exact moment.
Yeah, it changes based on the airplane's health, its weight, and the specific aerodynamic stays of flight you happen to be in.
It's a literal peek behind the long cockpit door.
Yeah.
And you do not need a pilot's license to find this absolutely captivating because at its core, this is a masterclass in high-stakes human-computer interaction.
Completely.
But to understand the extreme edge cases on the newer, heavier planes, I think we need to establish the baseline first, right? Like how the Airbus normal law actually operates day to day.
Yeah, let's define that baseline. So in the A320 family, the aircraft uses side sticks to command pitch.
So pointing the nose up or down.
Right. And roll, banking left or right. But those side sticks are not connected to, steel cables and pulleys that manually flap the wings.
Right. There's no mechanical linkage.
Exactly. They are connected to computers. When a pilot moves the stick, they are essentially sending a digital request.
A request. I love that phrasing.
Yeah. The computers interpret those inputs, calculate the physics of the aircraft at that exact millisecond, and then they send electrical signals to hydraulically activated flight surfaces to actually carry out the order.
So the pilot is basically voting on what they want the plane to do, and the computer decides the aerodynamic path of least resistance to make that happen.
That's a great way to put it.
But wait, let's say I pull the stick all the way back because I'm panicking in an emergency. Is the computer just acting as a nanny? Like, does it just restrict my input so I don't break the wings off?
It's actually the exact opposite. It's not a restrictor, it is an enabler.
Wait, really? An enabler?
Yeah, the notes draw a very crucial distinction here between a limitation and a protection.
Okay, break that down for me.
So a limitation is a structural boundary. It's a red line you must not cross, or the airframe literally physically fails.
Like game over.
Right. A protection, however, is an active system, like the alpha limit. It doesn't slap your wrist and say no. It says, I will give you the absolute maximum aerodynamic performance this airframe can handle, but I will physically prevent you from exceeding it.
Oh, wow. So if a pilot is like staring down a mountain in a sudden downdraft or something, they don't have to carefully do math in their head about stall speeds or G-forces while terrified.
No, not at all.
They can just yank that stick all the way back to the stops, and the plane will calculate exactly how to give them 100% of the possible lift without ripping the wings off.
Exactly. And if we connect this to the bigger picture, it's really about cognitive load.
Yeah.
Airbus designed this to provide what instructors call a stable platform. In a severe emergency, a human pilot just doesn't have the mental bandwidth to calculate those margins.
You're just trying to survive.
Right. By trusting the protections, the pilot's workload is drastically reduced when seconds matter most.
Okay, so normal law is this brilliant invisible co-pilot, handling the heavy lifting and keeping the plane in a safe envelope.
Yep.
But, eventually that plane has to touch down on a runway.
Right.
And the Earth is a very hard, very unforgiving physical limitation.
Dryly unforgiving, yes.
So if normal law is so good at maintaining a stable platform in the sky, how does a pilot actually get the plane onto the pavement?
Well, the aircraft actually has to deliberately alter its own logic.
Really?
Yeah, it has to force the human to take over the finesse of landing. This transition is called the flare law.
Flare law, okay.
Moving from flying in the sky to rolling on the pavement is like the most critical logic shift for the handling pilot. And what's crucial for A320neo and XLR pilots to understand is that this logic changes depending on the exact variant of the plane you were flying.
Okay, because the notes mention that on the standard A321neo, the plane introduces a slight nose-down pitch at 50 feet above the ground.
Right.
That sounds entirely counterintuitive. I mean, why on earth would the computer intentionally point the nose down right when the pilot's trying to pull the nose up to land softly?
I know, it sounds crazy. But it comes down to the aerodynamics of ground effect.
Ground effect. Okay, I've heard of that.
Yeah, so when an aircraft gets very close to the runway, the air underneath the wings gets compressed against the ground. It creates this cushion, a ballooning effect, that basically wants to push the airplane back up into the sky.
Oh, so it just wants to keep floating.
Exactly. If the computer kept flying the plane perfectly stable, it would just float all the way down the runway and never actually touch down.
That's a problem.
A big problem.
Yeah.
So at 50 feet, the A321neo applies a 2-degree nose-down pitch over 8 seconds. It artificially makes the nose heavy.
I see. So it forces the pilot to actively pull back on the stick to fight that nose-down command, which naturally brings the plane through that ground effect cushion for a smooth landing.
You've got it. You're physically flying it at that point.
Okay. But the master class focuses heavily on the A321XLR variant, right? Which is much heavier and flies longer distances.
Very heavy, yeah.
Wait, if the XLR is a heavier, more complex beast, shouldn't the computer hold on to the controls longer to, help the pilot out?
You would definitely think so, but it's actually the exact opposite.
Oh, wow.
Because of that heavy weight and the massive shift in aerodynamics near the ground, a rigid computer algorithm just can't feel the nuance of that air cushion as well as a seasoned human pilot can.
The computer doesn't have the feel for it.
Exactly. So on the XLR, the logic shifts even earlier. At exactly 60 feet on the radar altimeter, the trimmable horizontal stabilizer, the THS, completely freezes.
Okay, let's define the THS really quickly for everyone. That's the entire horizontal tail wing of the plane.
Yeah, that's the one.
The part that normally auto-trims to keep the plane level without the pilot having to hold the stick perfectly still all the time.
Correct. For the entire flight, that massive tail surface has been making these little micro-adjustments to keep the aircraft perfectly balanced.
And at 60 feet.
At 60 feet, that auto trim is dead. The aircraft reverts to what's called a proportional control law.
Proportional control law.
Yeah. From 60 feet down to the runway, the pilot has a direct, unadulterated stick-to-elevator relationship.
Man, it's like the training wheels suddenly popping off a bicycle right as you were navigating the trickiest final few feet of a steep, winding driveway.
It's a great analogy.
But the aerodynamics make it so much harder.
Yeah.
You've had all this help keeping the heavy nose of the XLR up, and then suddenly at 60 feet, the plane just says, you have the controls, good luck.
Right. And because that THS freezes higher up, the nose of the heavy XLR wants to drop much faster than a standard A320.
Okay, that makes sense.
The instructor's corner of these notes highlights a massive trap here for pilots transitioning to the XLR. They call it the floater trap.
A floater trap.
Yeah. If you fly the XLR passively, expecting the computer to help you flare like it does on the smaller variants, you won't pull back hard enough. That heavy nose will drop, and you will essentially smash onto the runway.
Ouch. And the notes mention the inverse of that, too, the pump trap.
Yeah.
Which I could perfectly picture this.
Oh, yeah, it happens a lot.
Right, like a pilot hits 60 feet, the auto trim dies,
Yeah.
and suddenly the stick feels completely different. It feels direct and mechanical.
Mm.
The pilot gets nervous because they lost that smooth, computer-assisted feeling. So they start rapidly pumping the side stick forward and back, just trying to chase the right attitude.
Exactly. Instead of applying precise, sustained back pressure to smoothly counteract that dropping nose, they over-control the aircraft.
They're just fighting it.
Yeah. It requires a fundamental mental shift to understand that at 60 feet, the plane is no longer helping you. It is actively demanding your physical airmanship.
That is wild. So at 60 feet, The plane basically surrenders to the pilot so they can finesse the landing.
Right.
But what happens when the plane's physical energy state is so critical that human finesse actually becomes a liability?
Yes.
Like we just talked about landing, but let's talk about a heavy takeoff or a go-around where you have to abort the landing and climb back out.
Mm.
In those high-stress moments, the automation actually violently takes the controls back, doesn't it?
Yes, it does. This brings us to the logic of protecting the energy state. Heavy A321 variants use a system called Enhanced Takeoff Configuration, or ETOC, to automatically optimize the exact angle of the flaps and slats for maximum lift.
Got it.
But the real lifesaver here, and honestly the source of a lot of simulator panic, is the alpha speed lock function.
Alpha lock. Okay, let's break down the mechanics of this. Alpha refers to the angle of attack.
Correct.
Simply put, that's the physical angle at which the wing is biting into the oncoming wind.
Mm-hmm.
If you point the nose too high, the wing bites too much air, creates too much drag, and stalls.
Exactly. Now imagine an XLR pilot is climbing out after a heavy takeoff. They reach the altitude where they're supposed to clean up the wing to fly faster, so they reach over and physically move the flap lever to retract the slats from position 1 to position 0.
Makes sense. You want to go faster.
Normally, yeah, the slats slide back into the wing, but if the angle of attack the alpha is currently too high or if the airspeed is too low, the alpha speed lock steps in.
Wait, it completely overrides the human?
It absolutely ignores the lever. The computer looks at the physics of the airflow over the wing and says, if I retract these slats right now, we lose our lift and we literally fall out of the sky. So I'm keeping them extended.
And the pilot screen just flashes, ALOCK.
Yep.
But this creates what the instructor notes call the broken handle panic. I mean, you're a pilot in the simulator. You physically move the lever to 0. You expect the slats to go away.
Right, muscle memory.
Yeah. You look at the screen, and the slats are still extended. Human nature just takes over. You start frantically jiggling the lever, troubleshooting a piece of plastic because you think the physical handle is broken.
It's a classic case of system fixation. The computer is saving your life by prioritizing the actual aerodynamic energy state of the aircraft over the mechanical position of a lever in the cockpit.
But the pilot doesn't see it that way in the moment.
No, because the physical interface doesn't match the aerodynamic reality. The pilot's mental model just breaks down and they panic.
So if jiggling the plastic handle is the entirely wrong move, what is the pilot actually supposed to do to fix an alpha lock?
The fix requires you to understand what the wing is actually experiencing. You pitch down.
Wait, what? You're climbing away from the ground, the plane is heavy, and you're supposed to point the nose down.
Just slightly. Yeah. You are currently demanding too much lift for your current speed. Your angle of attack is too steep.
Okay.
By pitching the nose down, you reduce that angle of attack. The wing slices through the air more cleanly, which allows the aircraft to accelerate.
Oh, I see.
Once the airplane reaches a safe speed and a healthy aerodynamic energy state, the computer realizes the danger has passed. It quietly releases the lock, and the slats automatically retract, just like your lever originally asked them to.
So you don't fix the lever, you fix the physics.
Exactly. Fix the physics.
That is such a profound way to look at it. But, this whole broken handle scenario brings up a terrifying thought.
What's that?
The automation protects the pilot in normal law, right? It saves them with alpha lock.
Yeah.
But what happens when the sensors feeding the computer fail? Like, how does the pilot know who is actually in control, and can the cockpit interface ever accidentally lie to them?
Well, this is where we get into abnormal law management. And the short answer is yes, the interface can absolutely misdirect a pilot if they aren't looking at the right screens.
Seriously.
Yeah, the masterclass notes highlight a vicious trap involving the yaw damper, or the flight augmentation computers, the FACs.
Okay, let's define the yaw damper first. That's the system that automatically moves the rudder on the tail just a tiny bit to stop the plane from wagging left and right like a fish, right? It keeps the ride smooth for everyone in the back.
Precisely. Now, if you lose that yaw damper system, or both FACs in flight, the main warning screens, the ECAM, which is the central health monitor, and the PFD, the primary digital windshield the pilot stares at, will both prominently display the words ALTN law in bright amber letters, alternate law.
Okay, so the plane drops out of normal law and loses its protections. That makes sense.
But that's the trap. It doesn't lose its primary protections.
Wait, really?
Yeah. Because of a quirk in the warning architecture, losing that one specific subsystem triggers the broader alternate law warning on the screens. But structurally, for pitch and roll, your stick inputs are still operating in normal law. You still have your aerodynamic protections.
Are you kidding me? So the plane's primary warning screen is literally screaming alternate law at the pilot, but it's basically tricking them. The plane is perfectly fine to fly normally.
It is a very insidious quirk. The instructors note that they constantly see pilots in the simulator read that amber warning, panic, and start bracing for a heavy, difficult, manual trim landing.
Because they assume all their protections are gone.
Exactly. But in this specific failure, the normal flare mode we talked about earlier is actually still fully available. They are intentionally spiking their own workload because they trusted a blanket warning instead of verifying their actual flight state.
Wow. Which is exactly why the notes hammer home the importance of the FMA, the flight mode annunciator, at the very top of the pilot's screen.
Yes, the FMA is everything.
The FMA tells you what the aircraft is actually doing at that exact millisecond, not just what a generalized warning system is shouting.
If you just react to the amber text without reading your FMA, you end up flying a much harder approach than necessary, basically fighting a ghost.
That is wild. But there are times when you are forced into actual real direct law, right, where the computer completely taps out and all the protections are truly gone.
Yes, unfortunately. In most serious failure cases, the moment you drop the landing gear with the autopilot turned off, the system automatically reverts to true direct law.
Okay.
Auto trim is completely dead. Your side stick deflection now equals the exact physical surface deflection on the wings. It is a total back-to-basics flying mode.
And this is where the instructors warn about the Togier pitch-up trap.
Oh yeah, this one is rough.
Talk to me about what happens if you are in true direct law. You're coming in to land, but suddenly something is on the runway, and you have to hit Togier, take off, go around, thrust to abort the landing, and climb out.
It is a violent physical reaction. The engines on an Airbus A320 family aircraft are underslung. They hang down beneath the wings.
Right.
Think of it like a heavy shopping cart. If you want to push a shopping cart forward, you push the handlebar at the top. But imagine trying to push a heavy shopping cart by kicking the bottom wheels forward.
Oh, the bottom shoots forward, and the whole front of the cart wants to just tip backward towards you.
Exactly. When you suddenly apply maximum Togier thrust, the physics of those underslung engines pushing forward from below the center of gravity creates a massive, forceful pitch-up moment on the entire aircraft.
And normally the computer would fix that.
Normally, yeah, the fly-by-wire computers instantly counter this pitch-up for you, but in direct law, the computer is asleep.
So if the pilot is passive, just waiting for the computer to fix it like it usually does.
The nose will pitch up so aggressively that the plane will rapidly approach a stall.
Oh my God.
To survive it, the pilot has to aggressively, physically push the nose down with the stick and frantically spin the manual trim wheel by hand to fight the sheer physics of the engines. You are literally wrestling the thrust.
That sounds exhausting. And there's one more trap in these notes that genuinely gave me chills.
The dual RA failure.
Yes. The radio altimeters. These are the sensors on the belly of the plane that bounce radio waves off the ground to tell the computer exactly how many feet are left until touchdown. What happens when both of those die?
This is honestly one of the most demanding scenarios an A321 pilot can face.
Because you don't know how high you are.
Well, yes, but it's worse. If both radio altimeters fail, the aircraft drops into direct law the absolute millisecond you select the landing gear down. But the real terror isn't just the control law changing.
What is it?
Because the plane no longer knows where the ground is, it can't trigger any of your automated audio callouts.
Oh, so there is no computer voice counting down 50, 40, 30 as you approach the dark runway.
Dead silence. And you lose the retard prompt that verbally reminds you to pull the thrust levers back to idle before touchdown. The cockpit goes entirely quiet right when you need information the most.
That is terrifying.
You are forced to rely entirely on your own visual terrain awareness out the window, and the FPV, the flight path vector bird symbol on your digital screen, to guess your flare height and manage your energy state. It requires supreme, fundamental airmanship.
So we've gone from the comfortable, cognitive-saving protections of normal law through the tricky 60-foot auto-trim drop on the XLR, past the traps of the broken handle, and into the silent, terrifying cockpit of a dual-sensor failure.
It's a journey, for sure.
How do the masterclass instructors synthesize all of this deeply technical aerodynamic theory for the pilots actually flying the line?
They basically boil it down to 3 golden rules for flight control.
Okay, lay them on me.
First, fly, navigate, communicate. But in the context of the complex A321XLR, flying doesn't just mean keeping the shiny side up. It means truly understanding your energy state. It means knowing that the wing might physically refuse to retract its slats, like with the alpha lock, to protect you from falling. Don't fight the automation. Understand the aerodynamic why behind what it's doing.
Right, fix the physics of the wing,
Yep.
not the plastic lever in your hand.
Exactly. Second rule, understand the FMA at all times. Monitor your guidance modes relentlessly, especially during the flare or during any reversion to abnormal laws.
Because of the traps.
Yeah, don't be fooled by a blanket warning like the yaw damper trap. Know exactly what your flight controls are doing at that exact second.
And the third rule.
Take action if things do not go as expected. If the pitch or the trajectory of the aircraft diverges from what you commanded, do not hesitate to troubleshoot the automation. Instantly disconnect the autopilot and fly the aircraft manually.
You know, you listening right now might never sit in the left seat of an Airbus A321XLR. You might never have to wrestle a 2GA pitch-up. But this deep dive into flight control philosophy is really a perfect metaphor for our modern lives.
Oh, absolutely.
We are increasingly surrounded by incredibly complex automated systems. Whether it's a self-driving car navigating a chaotic city street or, AI algorithms managing massive workflows at our jobs, understanding the underlying logic is crucial.
It's mandatory, really.
Yeah, understanding when the computer is actively helping you, when it's actively limiting you for your own safety, and exactly when it is quietly handing the controls back to you to make the final call. I mean, that is arguably the most important skill of the 21st century.
If we connect this to the bigger picture, the Airbus philosophy teaches us that we cannot be passive operators of complex machinery. The computer is an enabler, not a replacement.
Right.
We have to be active, deeply knowledgeable partners with the automation.
Which leaves us with a really provocative question to think about.
Let's hear it.
If we continue to design brilliant, highly complex systems that seamlessly shift their own rules to save us from our own mistakes, but those exact shifts create hidden traps, like the broken handle panic or fighting an underslung engine, that require incredibly specific, counterintuitive manual intervention to survive.
Yeah.
Does building smarter automation ironically require us to become much more suspicious, manually proficient humans?
That is the ultimate paradox of fly-by-wire and really of all automation.
Yeah.
The safer the system makes us in the normal envelope, the sharper, more fundamental our skills have to be when we inevitably fall out of it.
It really makes you think twice about that lane assist in your car, doesn't it? You're just waiting for the training wheels to pop off right at the trickiest part of the driveway.
Exactly. Keep your hands on the wheel.
Thank you for joining us on this deep dive into the Airbus logic. Keep questioning the complex systems around you. Keep checking your own personal FMA, and we will see you next time.